Hello, my name is Irene Abril Cabezas, and I am a final year PhD student at the University of Cambridge, where I work with Blake Sherwin. The focus of today's talk is that I would like to update you on the status of our quest for primordial gravitational waves with the Simons Observatory. So for the Simons Observatory, as a reminder, it really all revolves around the cosmic microwave background. The CMB was emitted only 400,000 years after the Big Bang, and it contains a wealth of information regarding the universe's initial conditions and composition. For example, primordial gravitational waves sourced by inflation should have left an imprint in the CMB-BB power spectra, which is the main focus of this talk. As an aside, let me also mention that the CMB acts as a backlight for the intervening large-scale structure, because on the way to our telescopes, CMB photons interact with this large-scale structure, and this generates the so-called CMB secondary anisotropies. That they also encode a wealth of information, such as neutrino mass, dark energy, or galaxy evolution. Importantly, this late-time evolution transforms E modes into B modes, which act as a source of confusion for B mode searches, and that we would like to remove in a process so-called delensing that we'll discuss briefly also in this talk. So, as I was saying, it really all revolves around the cosmic microwave background. We want to make these beautiful CMB maps and measure their power spectrum. So after WMAP and Planck, the CMB satellite missions, now ground-based CMB experiments, Simons Observatory, but also the South Pole Telescope or Bicephary, for example, are mapping the polarization component of the CMB and small angular scales with unprecedented sensitivity, which I am illustrating here in terms of these forecasted measurements for the CMB power spectra, TT, EE, and BB. Of course, we cannot do all of this science with a single telescope, and this is why we are an observatory with two surveys. So going back to the previous slide, actually, we have that for primordial fluctuations, BMOT is, we actually need deep maps with good control of the polarization systematics, whereas for this late-time science, we need high resolution and large-scale coverage to deliver our goals. So this is why we have the SO-SATs, the small aperture telescopes, which actually focus on large angular scales. These are deep maps, 10% of the sky with low angular resolution, because the dishes are 42 centimeters. And then we have the SO large aperture telescope, which focuses on small angular scale. This is high L. And then this will provide wide maps with high angular resolution. This is for 40% of the sky. This is we have a 6-meter primary mirror. So the B modes, then we will do with the SATs. This is small aperture telescopes, and then we will measure the CMB power spectrum. The BB power spectrum will be the contribution from this tensor mode sourced by inflation with amplitude parameterized by R, and then of course this lensing that I was describing whose amplitude we parameterized by A lens. So if we delens, this A lens will go down. Basically, that's the idea. So let me, and then in particular for the SATs, we're going after this recombination path at around L of 90, with which we will be able to test early universe physics. So I am very happy to show you now the initial science data of the SO-SATs. This is just a few months of data. We started mapping the sky with two mid-frequency SATs, which operate at 90 and 150 gigahertz. Here I'm showing a zoom-in region where we filtered the L's, high L's, both small and high L, so L below 80 and above 1,000, to make these QU patterns that describe the linear polarization of the CMB very apparent. You can see here these crosses, for example. Then QU are, we can transform into E and B maps. So I'm showing here this E mode map from the SATs, and then we take the power spectrum. both the 90 and 150 and the cross terms. The L ranges here are preliminary. We're still understanding our data, especially the pre-processing that affects the larger scales. And we've also, for example, haven't subtracted any EE dust contribution. I will discuss these challenges briefly later, but we are really excited and our detectors are already exceeding baseline sensitivity. So we are excited because actually now we're a 10-year survey because our initial 3 SATs are actually going to be extended to 6 thanks to the contribution from ESO UK with 2 SATs and the ESO Japan with 1 more SAT operating at lower frequencies. And so here I am showing the forecasted 95 constraints on the tensor to scalar ratio R, which means, and again measures this amplitude of the large scale B mode sourced by inflation, and the scalar spectral index NS that we will be constraint that will be achieved by SO. So, and then the black line shows the prediction from an R squared. This is the Starobinsky inflation for a total number of fields in the of 45, the small circle, and 75, the large circle. And so now the green quarters actually show the current 68 and 95% constraints from the bicep KEGG array, a combination with Planck and WMAP data. And so while current limits already exclude a set of single-role inflation models, there's a strong motivation to search for the signal predicted by certain large field plateau models like the Skarovinsky one. So, and you can see here that while the nominal ESO survey would not be able to detect this signal, the full 10-year ESO SAT survey could actually provide evidence at the 3 sigma of higher for these models. So let me now describe a bit of the challenges and how we're surmounting and how to make this detection or lack of a reality. So let's start. We'll discuss galactic foregrounds, instrument systematics, and also a bit of lensing. Let me start with galactic foregrounds. And so to illustrate this, I have this animation here made by the source Cosmoglobe collaboration. And you can see here that with millimeter experiments, we're actually let me play this. We're actually seeing, we're mapping the millimeter sky, and in doing so, we're actually seeing the galactic foreground emission. So at low frequencies, we're dominated by synchrotron. These are relativistic electrons spiraling down the magnetic field of our galaxy. And at high frequencies, we're dominated by dust. So the dust, still stars in our own galaxy emit UV radiation that heats up dust grains that then emit in the millimeter wavelengths that we're seeing. And the main takeaway basically is that these foregrounds are complex. They have a complicated frequency dependent and spatial properties. We have to take them into account into our analysis. CMB becomes the least contaminated at 90 gigahertz, but this is really something we're thinking about. And for B modes in particular, we're mostly worried about dust. And so for dust, what we usually say is that the spectral energy distribution, we usually describe it as a modified black body that tells you how the emission of the different frequency channels are related. And then we use these properties to then separate all the components, all the foregrounds versus the CMB. And so this pipeline for SO was developed by Kevin Waltz. You can read their paper, the SO component separation pipeline. We have different methods to separate the CMB signal for what is not the CMB. And indeed, and then we've done lots of work that incorporates the complexity of galactic foregrounds into our component separation pipelines. In particular, as I was saying, dust, for example, is extremely non-Gaussian field. It presents a filamentary structure that simply cannot be reproduced by Gaussian statistics. And so will it have an impact on R? And the idea is actually in this work that we find that R is actually completely unaffected, but the spatial dust parameters that describe this dust variation across the sky actually become degraded. And then this would affect your goodness of fit metrics. Then Andrew Liu last year actually then studied how dust this beta D that controls the SED parameters, so the different frequency dependence of dust, how its complexity might affect our inference, because this spatial complexity can actually induce decorrelation. So whereas different frequency channels are not just simply related by a modified black body. And so you can see here that our fiducial pipeline would actually create large biases when this beta D it has a big dispersion. But for example, the moments method, for which spatial fluctuations of the spectral index are parameterized by a Gaussian random field with a low power spectra, then this helps mitigate the biases. And this moments pipeline for SO has been developed by Susanna Anthony. And then, of course, if dust indeed present these large variations, then we are expecting that then we will have to use more flexible foreground models to achieve unbiased constraints on R. So these are the kind of things we're thinking about, and we are very careful when we have to do when we do our analysis. So now let me discuss a bit more detailed instrument systematics. And the idea here, the idea here is that the maps that we create are biased because of this time stream filtering, which just means that we want to remove sources of noise, and so just makes that bias our maps. And on top of that, there is no when we estimate the CL power spectra, this pseudo CL, there's actually no analytic formula to account for the mode coupling and polarization leakage in these pseudo CL estimates. And so the solution here is estimate this suppression of power and this with a transfer function that describes, as I was saying, this loss of power, and as well as the mixing between the different frequency channels due to time scale filtering. So using this transfer function method, Carlos Hervías, in a paper last year, we see that we can indeed recover unbiased constraints for our CLs at high L. At low L, less than 30, we see that actually these measurements are biased by more than a sigma. But when we actually include additional foregrounds and noise, then this bias is small compared to the statistical noise that we introduced. So then indeed, we show that our spectra is unbiased, and then this pipeline then is now validated, and we're going to use it for the first 1 or 2 years of Simons Observatory SAT data. Of course, you might also worry about the intrinsic beam dependence. The idea here is that CMB telescopes observe radiation of a wide frequency bands instead of just a monochromatic frequency channel. So it's natural to expect some variation of the beam properties within each band. And then, of course, it's further complicated because of the frequency dependent of the sky components, galactic dust, for example. And then you might have beam non-idealities that are present. And then the idea here is that we have to quantify these effects. So Nadia, also in their paper last year, we find some negligible bias on the sigma R, so on the measurement error on R, and a very small bias, less than 0.02 sigma bias on R. So this is super promising, and we believe now that our pipelines are starting to really be ready for the SO science data. And let me discuss finally lensing beam modes and what we're doing about them. So the idea here is that the weak gravitational lensing of the CMB results in a direction-dependent remapping of polarization anisotropies, and this causes part of the E-mode signal produced by scalar fluctuations, not tensor scalar, to morph into B modes. So although lensing-induced B modes, let me have simulation, next slide. Yeah, these lensing-induced B modes are not expected to bias our primordial gravitational wave measurements because their power spectrum is well constrained and can be accounted for. Their contribution to sample variance, then this would increase our statistical uncertainties on R, which is a problem. So the idea here is that we can use an empirical proxy for the CMB lensing convergence field, and then actually reverse the deflection caused by this weak gravitational lensing of the CMB. And this is the phenomenon that we call delensing. And that the improvement on sigma R was actually first demonstrated by Kimi Wu in this paper of the bicep, Keck, and SPT pole collaborations, where you can see now that actually there was an improvement on R going from 0.09 to 0.082 with 95% confidence. These are upper limits, thanks to D-lensing. And for the Simons Observatory, Emily Hertig has been developing the pipelines to also do D-lensing using of these B-mode measurements. And you can see here that the improvement is between 30 and 40% on the error bar on sigma R, and also for a variety of foreground models, which is also something we have to take into account. So this is super promising, and we think that with this, we're actually gonna be able to reach our forecasted constraints. The pipelines are there, and we're really working on this. We're gonna be able to place, again, very tight constraints on the sensor to scalar ratio with the Simons Observatory, because the future is actually extremely bright, right? We survey actually will now run for 10 years. We're gonna achieve a constraint thanks to this with 3 aperture telescopes, but another 6 small aperture telescopes on 6,000 square degrees, a sigma R of 1.2 10 to the minus 3 that we forecast. And then also, if you're interested in the lab science, we're actually gonna map half the sky with 2.5 microkelvin arc minutes. So really stay tuned for upcoming results from both surveys. It's really, really exciting. And with this, let me finish, and a huge shout out to all the Simons Observatory collaboration members and all their hard work that I was really fortunate to present today. Thank you for your attention.